so you guys know I love the chemistry section. This is my favorite part, mostly because you get to do fun stuff like blow up a piece of sodium in the fume hood. You have a great story to tell about it, right? So hopefully we'll do two other lab activities over the next little while. We'll do one later this week where I have you guys actually go around and mix some solutions, and I might even have you mix those solutions with other solutions. We'll see. I haven't quite figured out. Hey, are you sticking around? Okay, just throw it on the. Thanks. Um, I'll have you guys. We'll figure out the lab for later, but I want to do something on Thursday where you kind of get hands on. Rather than me do the work, though, I want to have you guys do something with it. And then we'll do another activity later in the unit where we essentially try to make a battery out of chemicals. Because really, that's what a battery is, right? A battery is some chemicals that you put together and it makes an electric circuit. So, but anyways, we got to build our way up to that. So I'm going to start this as though it's topic 4, just because Kelsey kind of did topics 1, 2, and 3, so I just figured we'll make this number 4. So what we're going to talk about today is kind of the first third of our unit is on solutions. What's a solution? That's actually like the best definition I can imagine. Some stuff mixed together. Like I know it's not the most technical. A solution is made up of. Sorry, I have my spinner now. I fidget too. A solution is made up of what's known as a solvent and a solute, and I have those down here at the bottom. But like really, Belka, your definition is more or less what this is right here. Some homogeneous mixtures composed of a solvent and solute is really a fancy way of saying stuff gets mixed together, right? What is your stuff though? Well, you always have to have a smaller amount of stuff get mixed with a bigger amount of stuff, right? So in terms of definitions, the solvent is always what there is more of, and the solute is always what there's less of, and when you mix the two things together, you have what's known as a solution. So in terms of definitions, I need you guys to know words. Solvent is the bigger item, solute is the smaller item. 9 times out of 10 in the chemistry lab, no, more than that. 99 times out of 100, I bet. The solute is water. No, the solvent is water. And the solute is some sort of solid. But it doesn't actually have to be like solids getting mixed into liquids. That's just one of the possibilities. But since it's the most common one that we work with, I think this picture kind of shows really well. But let me give you some other examples of substances. Syrup, for example. Right, that's actually a solution. I mean, it's not necessarily just water. I mean, there's a crap load of sugar all shoved into syrup too, right? But like even pop's a good example. That's a solution for a couple of different reasons. Sure, there's the sugars being dissolved in the water, but there's also carbon dioxide in the pop. You know, like when you crack the lid, it goes like shh, right? And all the gas gets released. There's also gas dissolved inside of there. Cleaner is another good example. So here's the definitions I just gave you then, right? Solvent is the medium. Do you guys know the word medium? Another word for stuff. Technical word. Like if I were to ask you the medium in which your pop is dissolved, it's water. Whereas maybe in something else, the medium could be alcohol, perhaps, for example. Sometimes chemists will use some sort of alcohol to dissolve their solutions. Not like booze alcohol, but like just a generic term of alcohol. So, solute is the thing that gets dissolved. Do you guys know these definitions? Pure substance mixtures. You guys heard these words before? Right. Homo and hetero. I mean, we use those as prefixes more for like sexuality nowadays. But in terms of science, homo means the same, hetero means different. Right. So here's a picture just of kind of some examples here. If you've got all your matter, you've got your atoms and your molecules. They make up substances or mixtures. So like, let me just walk you through the 4 pictures here. If it's an element, literally everything is the exact same thing. Right? All you have is carbon, all you have is oxygen, all you have is nitrogen. There's no multiple things, right? Compounds are like, say, water, where you have like H2O and H2O and H2O and H2O, right? Where you do have more than one element, but really it's just that same thing over and over and over again still. Right? Whereas mixtures, like for example here, if it's a homogeneous mixture, you really can't see the difference. But you see how there's like no uniformity to this pattern? Here there's like 1, 2, 3, 4 of these guys here randomly, then there's 1, 2, 3, 4, 5 of those guys there randomly. You don't really see the difference in a mixture like this. It just kind of all looks the same in a homogeneous mixture. Whereas in a heterogeneous or heterogeneous, however you say the word, you can actually like literally see the difference. For me, this mixture right here is like nuts and bolts. You know how like you guys ever do this at Christmas time? You get like the the Shreddies and the Cheerios and like the pretzels and stuff like that, if you can literally see the differences between all the items in there, then it's a heterogeneous mixture. Whereas like Kool-Aid is a homogeneous mixture because you can't actually see the different things inside Kool-Aid, but clearly there's like the color stuff, there's the sugar, there's the water, like there's stuff mixed in there, right? But you can't see the difference anymore. Is that clear? Sweet. Okay. Okay, so here's a slide I have just talking about some of the different ways that you can have solutions. It doesn't have to be solids and water. So I make this slide here just to kind of illustrate the idea that you can have anything, like for example air. Air is actually a solution. Most of air, the solvent, is nitrogen. About 77% of our atmosphere is nitrogen. The remaining bit is like oxygen, carbon dioxide, argon gas, and also methane gas. Right? So really, oxygen that we breathe and nitrogen is a solution of air. But you can have this in everything. You guys ever like pour a cup of water and like there's some bubbles in your water? Well, that's because you have oxygen in water. That's a solution, right? Or ice. You get a bubble underneath the ice. Antifreeze, which you'd put in like in the, well, not in the engine of your car, but like that you'd use to cool down or heat up your, keep regulate temperature of your vehicle, is actually methanol dissolved in water. Syrup is sugar dissolved in water. You can even have things called alloys. Ever heard of these before? Alloys are basically where you melt two different metals together, like say bronze. Bronze is mostly copper, and you melt some tin in it. And then when you like heat it up to like 2,000 degrees Celsius and melt them all together, then it makes bronze, right? Or what's another good one of those? I'm blanking on any other ideas like that. But you've heard of those before? Well, it depends on what they are. Like when bronze was discovered, bronze was actually stronger than tin or copper by themselves. Pure copper or pure tin wasn't that good, but bronze was even better if it worked like that. So, but it depends on what you melt and what, because some stuff might not actually adhere or adhesive mix. Yeah, you get the word. So, okay, here's the thing I need you guys to know. We often put a little bracket next to it to let you know what you're dissolving it in. And I'm almost certain we've talked about this AQ thing before here. AQ means aqueous. It means you're dissolving it in water, which in our chemistry lab, like 99 times out of 100, we're dissolving it in water. But in theory, we don't have to. You could dissolve something in, say, an alcohol. I don't know whether he has any, but like a biology teacher like Lav might have like a cow's head or an eyeball maybe preserved in, say, like formaldehyde. You guys ever seen those sorts of things? Or like a fetal pig in like a jar? Yeah, I don't know that he has them in the new building here, right? But that would be a good example of sometimes we dissolve things not in water, we dissolve them in alcohol. You guys remember how when I did the sodium in water experiment and it blew up? I probably never showed you it all that well, but the sodium sticks were kept in a little container, and they were kept, I don't want to say moist because moist I think implies water, but they were kept in fish oil. Because imagine that big chunk of metal there. If I had just left it in water, well, it would blow up right in front of you, right? So yeah, you actually have to dissolve it in like an oil or something along those lines to keep it safe. Okay, anyways, another definition I need you guys to know is a term called an electrolyte. You guys ever heard the term electrolyte in like everyday life scenarios? Yeah, that's the one that comes to mind. Yeah. If I remember the story correctly, the University of Florida back in the 80s, 70s was trying to create a drink that would help their athletes do better. Because like athletes, they often use the phrase like you want to replenish your electrolytes. When my daughter gets really sick and like she's throwing up all the time, we go down to the store and we get one of those like pediatric solutions to try to like help her get back her electrolytes back in her. Long story short, electrolytes are things that get dissolved in liquids typically, right? And the idea is that you want to have them, and as a human, one of the reasons why is that they allow you to conduct electrical current. And I totally spelled the word current wrong here, by the way. That's current. We need current. Okay. Electrolytes, basically they conduct electricity. Okay, now that's the chemistry definition. From like the Gatorade definition, yes, they do that as well. Gatorade's more about like replenishing ions in your body's, like the water that your body maintains. Right? But long story short is that they conduct electrical current. So what I want to do on Thursday in our activity is I want to actually show you the idea of electrolytes. The idea basically being that if you were to like run a battery sort of cell through a beaker of the solution, if no current flows through it, then it's not electrolyte. Whereas, like, if you can get a light bulb to turn on, then there must be electrical flow allowing through it. Now, I want to make sure this picture's clear here. What you do is you put, like, one piece of metal in the water, but you you don't touch the pieces of metal to each other. They are kept separate. And then you try to run like a battery and a light bulb through it, and what should happen is the current would run. Of course, this thing just shut up. It's dumb. Come on. There we go. No, I don't think so. Maybe it is actually. Whatever. My wireless thing seems to crap out about half the time. So I'll try to show you guys this on Thursday, the idea, but hopefully you can see in the picture here. Is it working? Come on. There we go. Okay, these two pieces of metal right here, they are not connected. So it's almost like my headset right here. From here to here is not connected in a full circuit, right? And for electricity to flow, you need a full circuit. If I were to dump this in water, then it would actually connect a current from here to here. It would then run through the wire back to the other side and continue the loop. That's so anyways, long story short is that that's your test for electrolyte solutions. If you can actually have electricity run through the solution, then it's an electrolyte. If not, then it's not.
Like tap water.
So tap water would be an electrolyte, but that's because tap water actually has stuff dissolved in it. Yeah, like there's chlorines, trace amounts of iron and sodium. If you had what's known as distilled water, like pure water that you might buy in the store, it should not conduct electricity. Which is why like the whole putting the toaster in the bathtub sort of thing, that is dangerous, obviously. Yeah. But that's because you're using water that has the ability to conduct electricity. So like distilled water. Pure water should not, yeah. So I want to try to show you guys that on Thursday in our activity. I'll try to make some. Really, water on its own is not a solution, because for it to be a solution, there has to be something inside of it. But hopefully, I'll be able to show you tap water versus distilled, and you'll be able to see, oh look, this one makes the light bulb light up, this one doesn't. You know what? Let's actually do a quick demo on that right now. Stuff is too loud, so you have to bear with me a minute. Oh well, I don't mind that. Did you guys ever see these sorts of things last year in my chemistry class? That's a fine CD heater. Okay, so I just put some tap water into this beaker right here. So this has got tap water. I mean, basically the way this test works is that, see how these two things are not connected to each other, right? So if I press the battery on it, it says on, right? If I put it into there, does it do anything? Yeah. So what do we get up to? Okay, so ideally what this means is that this is conducting electricity, right? What ends up happening is it's completing a loop literally through the ions that are dissolved in there. Hence, this is an electrolyte. So that's tap water. Now, this, I hope this experiment works here. This is supposed to be distilled water. So this is not actually a solution anymore. There's only literally water in it. Now, this may script because this isn't a clean beaker or anything. But let's see. Hopefully what happens here, you see how the light is on 1. There's no conduction happening through this one. Same thing in this water. We're up to 5. Does that make sense? So that's the difference between pure water, where like literally the only ingredient in this is water, It actually says on here dissolved mineral salts, 0 parts per million, fluoride ions, 0 parts per million. Have you ever heard that phrase parts per million before? Um, parts per million basically just means that there's like 1 out of a million molecules would be like an iron or something like that. So you have 999,999 waters, and then you'd have 1 iron, which like at the grand scheme of things is not all that many, but it's enough to cause this stuff to conduct. Does that make sense? Okay. Anyways, long story short, ionic compounds are electrolytes. And that actually makes a lot of sense because ionic things, like say sodium and chloride, and how sodium has a positive and chlorine has a negative, well, that kind of explains how you can have positive and negatives inside your solution. See this little picture here, how like positives and negatives are able to kind of interact? If you have positives and negatives, they can move around and they can continue to flow. Whereas here, where it's just pure water, nothing is positive, nothing's negative, it can't continue electricity flow. So, ionic things are able to. There are some molecular compounds that conduct electricity, but not all. So it really depends on which one there is. So, okay, let's talk about the big word for the day. It's called dissolving, or sometimes you might hear it called like dissolution. Dissolving would be the best word to use. Okay? This guy in 1887, Svante Arrhenius, had this idea that really what's happening, and I love this picture, is that water is able to like rip apart solid stuff. So imagine this is a picture of something solid, like just your basic table salt. You guys have dissolved salt in water before, right? Like, you know, it's the basic thing you do when you're cooking, right? You put the solid salt in the water, but like it disappears, right? Just like Kool-Aid crystals. The reason why is that all of these positive and negatives that are being formed in your salt right here are really getting ripped apart by all these water molecules. See all these like HOHs right here? Those are water molecules. The analogy I like to give to my chemistry classes is imagine that there's just the 5 of us right here, and that we are all particles on salt. Okay? We're fairly strong, and if we wanted to, we could stay together if we wanted to, right? But imagine that in the classroom, all of a sudden we let in 1 million first graders. Now, on my own, I'm not really afraid of a first grader. They're really low. Let's say there were 1 million, right? Could you take 1 million first graders? We'd probably get separated, right? Or another analogy would be, I went to Gillette Stadium to watch a Patriots game, and like I'm standing with my brother and my dad and stuff like that. We're all trying to stay close together, right? And normally on our own, we can stand next to each other, no problem. What's going to separate us? Unless one of us chooses to walk away, nothing happens there, right? We go to Gillette, and there's now 70,000 people all there, and we're trying to walk away, and slowly but surely we get separated as we're trying to walk through the crowds because there's 1 million people there. You get kind of the concept I'm going for here? Well, that was Arrhenius' theory when it came to these particles right here, is that really what's happening is the positive and negatives are getting split up, and they're getting surrounded, they're getting like absorbed in a way by all of these water molecules. And it causes there to be negatives and positive ions inside the water, separate. Right? And that's what we're observing inside here, is even though I can't see them, basically there's a whole bunch of positives and negatives inside there that are being ripped apart by the water molecules. And so the name we use is dissolving. And that now explains now why ionic things conduct electricity. So, I mean, here's more pictures kind of describing what I just talked about here. An aqueous solution, then, is a solution that has water as the thing we dissolve. And we usually use AQ. That's kind of the little subscript for it. So, if I go to the back of my lab and I grab like a bottle of stuff that's solid, if it's still in its solid format, that's fine, right? But if I take it and I scoop it in and I put it in a beaker and I stir it all up like I would have done last 2 weeks ago, well, then we put the aqueous designation next to it instead. So, one more really cool thing about aqueous solutions, if you were to try to filter them, it would actually go right through the filter paper. So, like, if I were to run this water here through a piece of filter, nothing's going to get caught in the filter, because really what ends up happening is those particles are so small they go right through the paper itself. They're not solid, they've been separated into pieces. So here's another word we use to describe this. We call it solvation. But, I mean, really, the word you can use is just dissociating or dissolving. Those are good words to use. Okay, here's another picture just to kind of describe the same sort of concept, but I'm gathering you get the concept, right? This is what a solid chunk of salt or sugar or something would look like, right? And slowly but surely, the 1 million first graders come and rip it apart, right? And so this one's right here. Here's one more thing I got to point out, though. you need to have these water molecules right here to maintain it kept apart. What ends up happening is if you leave the solution out on the counter for a while, and then it evaporates. You guys ever seen like the recrystallization where like some solid stuff ends up reforming at the bottom? I'm gonna try to show you that as part of our lab maybe on Wednesday, Thursday as well. We'll make a solution. We'll let it sit out over the weekend, and after the water evaporates, then all of a sudden you'll re-see the solids forming again because as the water's gone, well then the positives and the negatives they reattach back together and they remake a solid chunk of whatever salt. So, have you guys ever heard this phrase before? Like dissolves like. I don't know that we would have done this in chemistry last year. Okay. Basically, the idea is that if something is polar meaning that it has positives and negatives, it can dissolve other things that have positives and negatives. But if you have something that's not polar, where there's like no like disbalance to it, like things that don't have charges, then non-polar things dissolve non-polar things. So, summary here: if it's polar, it dissolves polar. If it's non-polar, it dissolves non-polar, but you can't have one of each mix, which kind of explains this next picture here of oil and water. You guys ever like seen a picture of like, or been in a boat maybe, and you spill some gasoline or some water on top of the surface of the water, and they do not mix. If I were to go get like some canola oil from Blair and pour it on top, maybe you've seen this before. Like it literally will sit on the surface, and if I stir it like crazy, it will not mix together. They will separate. Okay? The reason is due to polarity. Water is considered a polar molecule. It has positive and negative ends to it. The hydrogen end is very positive on water, and the oxygen end is very negative. And due to that, water being polar can rip apart other things that have positives and negatives. Oils are not polar. They don't have a positive and negative end to it. So oils can dissolve other oils, and waters can dissolve other polar things, but not one of each. It's actually one of the basic principles behind how like say dishwashing detergent or like Tide for washing your clothes works, is that you need to have water to dissolve anything that's polar, but they often put in like an oily substance because the oily substance will dissolve anything that you spill on your shirt that's not a polar substance. Does that make sense? Anyways. Okay, I think we're almost at the end here. Is this my last slide or something? No, I still have the pages after this. Oh, I have the pages. Okay. Here's some other words I need you guys to know. Agitation, temperature, and surface area. Do you guys know it? Okay. You have something in your eye. Do you guys know what agitation means in chemistry sense? Like in your eye. That's what it would mean if it was not in the chemistry sense. Agitation would be stirring, basically. If you agitate something, you're mixing it together. So these are the three things that affect how well something dissolves. So like, again, think of like cooking example. If you were trying to make Kool-Aid, for example, Blair gives you like the big mix of Kool-Aid stuff, and he says mix it all together, right? Well, if I were to take the big thing of water, right, and I dump in a whole bunch of scoops and I just leave it like that, it's going to clump together. It's going to be the grossest Kool-Aid in the world, right? So the three main ways that we can get it to dissolve, first one is to stir it. That makes logical sense to everybody, right? If you stir it, it breaks it up better, it dissolves better, right? Another one is temperature. The best example I can give for temperature is how we make our coffee. Okay? If you have a higher temperature, things dissolve better. If you have a lower temperature, they don't. So when we make our coffee, we're really dissolving coffee grinds into water, but we boil the water first. Because another way you can make coffee grinds is you could pour the water through cold water through coffee and then heat it up. But that would be the most disgusting coffee ever. It would be so weak. You know what I mean? So like when you make your tea and you make your coffee or your hot chocolate, we boil the water first, then we add the stuff we want to dissolve in later, and it dissolves so much better. And one of the reasons why is that temperature just means that your particles are vibrating faster and they're moving faster. So it's almost like it's stirring itself. Does that make sense? The hotter that something is, the more that it moves, the more that it mixes stuff. The last one's surface area. If you were to dump like a chunk of solid metal, or like, think of like a sugar cube. You know how you can make like sugar in like cube formats? Put the sugar in the water? It would eventually dissolve. But you know what works way better? Is if you crush it up and then dump it in. Right? If you crush it up before you mix it in, then it's going to dissolve better. So I think all three of those things make a lot of sense. Stir it dissolves better. Heat it up, it dissolves better. Crush it up into pieces, it dissolves better. So, pretty intuitive. Okay, most of what we've just talked about here then is like just theory and definitions of words. Now I want to show you like something we can do with it. And so this is a new type of equation. Before Kelsey left for the Easter break, she would have taught you guys about the 5 main types of chemical equations you've learned about so far. You guys remember the 5? Formation.
Decomposition.
Good. What's
Hydrogen.
hydrocarbon combustion? Single formation, decomposition, single replacement, double replacement, and hydrocarbon combustion. Those are the 5 types of equations that you should have learned about so far. This is going to be the 6th equation we learned. This is known as a dissociation equation. And you're going to like these because they're drop dead easy. Like, I'm pretty sure I can teach you in grade 6 to do this. I don't mean to be insulting, but like they're really easy. There's not much to them. All you do is you take a ionic compound, which is solid, you write an arrow, and then you break it up into 2 different pieces. But you know how like when you write a compound, you don't really put the positives and negatives there together anymore? Well, what we do is we separate them into the positive and negative portions. And all you have to do afterwards is put the AQ, meaning that you've dissolved it in water. That's it. It's like the easiest equation in the world, these dissociation equations. Let me do another one here. If I gave you potassium hydroxide and we added it to water, it would make potassium, it would make hydroxide. Water is literally ripping this thing apart. The potassiums are positive, the hydroxides are negative, and for the state of matter, we just have to say they're aqueous. That's all. So like they are really, really easy equations to write. Sound good? Okay, so let me show you some examples here. Here's KCl going into K plus and Cl minus. That's pretty straightforward. But the next 2, I got to show you just a little, the one thing you might screw up on. So maybe I was making it sound a little bit too easy. There is one way you can screw up. See how there's a 2 right here for the aluminum and a 3 right here? Because you need 2 and 3 of them. Well, it means that you better put a 2 over here and a 3 over here, otherwise it wouldn't be balanced. Now you don't put the 2 afterwards like this. You put a 2 in front, saying you have 2 aluminum ions. And here you have 3 sulfate ions, which is really this 2 and this 3 right here. Or this one right here, this copper nitrate that you have going on right here. There's 1 copper for 2 nitrates, so you need to have 1 copper for 2 nitrates. With my chemistry classes, I use another analogy of this one here. It's with my daughter and cleaning up her toys. Imagine she's playing with like Barbies or Legos or something like that. And let's say that the Barbie or the Lego is put together. Right here, there is 1 item. This is her with her, let's say her Barbie doll all together, right? But then Kinsey and Cammie decide to go play, and they rip the leg off of Barbie, and they rip the arm off of Barbie, and they rip the head off of Barbie. And now there are smaller pieces scattered everywhere. Well, now there's not just 1 piece over here anymore. Now there's like 2 and 3 pieces. There's now like 5 pieces, but there's smaller sections of it. Like there's chunks of it. This is 1 complete molecule, or like 1 complete Lego toy. And instead, it's now been ripped apart into 2 of these and 3 of these. Get the concept? There's no law of conservation of molecules. That's not a thing. So like you can have 1 right here equaling 2 and 3. Essentially, you can have 1 turning into 5. It's just it's 5 smaller pieces. Does that logic make sense? Okay. Oh wait, one last thing here. Those equations, those dissociation equations, only work for ionic solutions. Because ionic solutions can break up into positives and negatives, and therefore they can conduct electricity. But if you have non-electrolytic solutions, then really nothing special happens. So it's like the most boring equation in the world. This is like a sugar in a solid form, and now it becomes a sugar in an aqueous form. And literally there's nothing to break it into for positives and negatives because this isn't ionic. Do you guys recall the difference between ionic and molecular? How do you know the difference between an ionic and a molecular compound?
Two gases or something like that.
Molecular is usually 2 gases. That better way of talking about it would be a metal and a non-metal. If you have a positive metal and a negative non-metal, then they can like positive and negative can suck together to become a neutral sort of thing there. But it's also possible to have multiple negatives all fit together, like say carbon dioxide, or like anything involving like the dis, the tris, the tetras, those prefixes, If they're all negatively charged, those make a covalent compound. But if everything is negative, then there's not a positive to be its like doppelganger, so that it doesn't actually turn into a positive negative kind of half thing. You guys recall that at all? It's been a while. Let me do an example. Can you see the little things I put on the board back there? Here's a great example of a ionic compound. Sodium and chlorine. Sodium over here is a plus one. Chlorine over here is a negative one. So a plus one and a negative one, they just fit together perfectly. Let's say I picked calcium, and I want calcium to go with chlorine. Now, these are still ionic because it's still positive and negative, but it doesn't fit quite as well because calcium is plus two and chlorine is minus one. So what do I have to do to balance this? Yeah, I need two chlorine inside, which means that it's actually CaF2. But it's possible to have a compound like this one here. Let's do this one here, S and O. You can go SO2. That's known as sulfur dioxide. If you ever smell sulfur dioxide, you'll recognize it. It's like that rotten egg. Horrible, horrible smell. It smells disgusting, right? Rotten eggs, basically. You ever smelled that before? You will. I don't actually want you to smell it because it's disgusting. But you see how this guy right here is negative 2 and this one's negative 2, though? That would be known as a molecular compound. And then that's where you start using the dis and tris. So as it's written right there, that would actually be sulfur monoxide. But if it was like SO2, it would be sulfur dioxide. SO3 would be sulfur trioxide. That makes sense? Long story short is if they're both negative, they can't split apart into positives and negatives. Let's see how these ones right here. There's a positive and a negative. These things are ionic. They will dissociate. They are electrolytes, and so therefore they conduct electricity. Make sense at all? Okay, so kind of quick summary of the day then. Most of it's really words. I mean, actually, you guys don't have to write a whole lot. Let's add a little bit here. You either have things that are electrolytes or things that are non-electrolytes. Those are basically the two categories. Electrolytes or non-electrolytes. Well, let's talk about them. What do electrolytes do? They conduct. Hence the name electrolyte, right? They conduct electricity. Non-electrolytes do not conduct. Intuitive sense so far, right? Why do electrolytes conduct then? Well, they conduct because they have positives and negatives. If they have positives and negatives, they conduct. What sort of compounds have positives and negatives? Ionic compounds have positives and negatives. Why do these guys conduct, or why do these guys not conduct? Well, it's because they don't have positives and negatives, which means they must be only negatives. These are known as those covalent. Covalent. Or the other word we use is molecular. So let me give you an example of each here. An ionic compound would be NaCl. It has the ability to turn into Na plus and Cl minus. Because it's got positives and negatives. Carbon dioxide. Carbon dioxide, if you put it in water, does not have the ability to split up into, like, say, carbon plus and oxygen negative. Like, that doesn't happen like that. So therefore, if you, like, bubble carbon dioxide through water, it doesn't conduct electricity. Like, carbon dioxide doesn't conduct. Which is probably a good thing, because you know how, like, carbon dioxide is a big part of our atmosphere? If I were to have these two wires sitting here, and I were to turn on the button here, if I breathed on it with carbon dioxide, it should then conduct electricity. Well, it doesn't. which is probably good because otherwise you just randomly start having sparks and electricity forming anywhere. Does that kind of make sense? Now I cheated a little bit on this example here though. What we should do is we should say this was a solid, and it's now aqueous when it's done. That's what you should be writing. You got to make sure you write that little subscript, because if it's not in water, water is what really rips the whole thing apart. If it wasn't for water, it would just do nothing. It would just sit there. So water is like the first graders that kind of a million first graders are going to separate you apart from your friend. Or like 70,000 Patriots fans will maybe make you get lost from your friend. Oh yeah, that's my lesson. Make sense to you guys? Okay. I gave you an assignment. Why don't you guys find out a question off the assignment? I just want to try one or two of them together with you, make sure you get the concept here. And I'll give you the rest of class to kind of work on stuff. So, the first couple of questions are really just review things. So, like for example, this one right here, an atom has an atomic mass of 9.01 and an atomic number of 4. Who's got a periodic table here, right? Anybody got theirs with them? What does an atomic number of 4 mean? How does that help you? Go for it. Atomic number of 4 means it has 4. Yeah, you're right. 4 protons. Okay, so Jason, you got a periodic table there. Which one has 4 protons? Hydrogen has 1. Helium has 2. Lithium has 3. So beryllium is 4. There you go. Determine the identity of this atom. This must be beryllium because it's number 4. Here, why don't we do this one together? Let's do it together as a group. I want to make sure you get this. You only got Lucy. There's probably some of those in that bin right there under the incomplete test section. Perfect class today.
I just really don't feel like going.
These things really are addictive. Alright, so you guys are all okay with the idea that by telling you the atomic number of 4, that means that it must be beryllium, because beryllium is number 4?
Don't know how to spell beryllium, you know?
Do you guys need periodic tables? Do you have your data books in there? Should be in there. Oh, okay, so open the book.
So much work.
Rough life. Work our way back in while it is.
Such a messy book.
Neutrons. Okay, so let's talk neutrons here. We know it has 4 protons, because literally that's the definition of what makes it beryllium. It's 4. But neutrons are what gives it the rest of its weight. Now its total weight was 9.01. How many do you think how many neutrons does it have? 4 of them have to be protons. 4 are protons. It has a total weight of just over 9. 9 minus 4. Yeah, be brave. I'm not going to yell at you if you make a mistake. Now, why is it not 9 right on the dot? Why is it 9.01? Some of them have 9, some have 10. But what ends up happening is like most of them probably have a weight of 9. A few have a weight of 10. And so like that's kind of its average. So the most likely number of protons or neutrons is probably 5, because 4 plus 5 gives you 9. But it doesn't have to be 5. It could be 6 or 7 or 8. Because do neutrons change the type of material you have? Only protons do. If you add more protons, it changes what it is. So you can add as many neutrons as you want. Right? All it does is it just makes it a heavier item. Okay, we haven't done this since last year. Do you guys know what a Bohr diagram is? Let me draw you one, just because it's been a while since we did this. This is what a Bohr diagram looks like. You usually draw like a nucleus like this, and in the nucleus you write out what you have. So because it's beryllium, I would say you have like say 4 protons, and I usually just do this like 4p+. It's a good way of saying this 4 protons. And then what we start doing is we start drawing out like dotted circles around it, something like this. I just keep drawing more and more circles for all the electrons to go in. Does this ring a bell?
Yeah.
Do you guys know how many electrons go in the first circle? 2. Yeah. And since this thing has 4 protons, it has to have 4 electrons. So I'd put like 1 electron and 2 electrons in the first circle, and that's the first circle. It always gets 2. Do you remember how many electrons are allowed to be in the second circle? 8. 8's correct. Yeah. Now, do we need all 8 though? How many do we need in the second circle? 2. Because there's 2 in the first circle, and there's 2 in the second circle, and so now we have a grand total of 4. What happens if you needed to have, 9 or 10 electrons? Well, then you just move to the next circle. Does that ring a bell? Another way people sometimes write it is they do it with like a line. They might say like 4 protons, like this, and then on the first line they'd say there's 2 electrons, and on the second one they'd say there's 2 electrons. Is another way of drawing it. Does that ring a bell? Okay. I know you've done it before because I taught it to you last year. You haven't used the words a lot. The other one's called a Lewis dot diagram, and I'm not sure I showed you this one last year. Basically, the way a Lewis dot diagram works is that you only draw the valence electrons, the outsidemost ones. So if this is beryllium, how many outside electrons does beryllium have? How many are in its outer layer? 2, yeah. So what you do is you draw 1 dot for each of the electrons. I think I might have showed you this once before, but I don't know that I ever used the words for that. So these 2 dots refer to these 2 electrons. That explains why beryllium has a +2 charge, because it wants to get rid of these 2 electrons. If it gets rid of those 2 electrons, then it's lost the electrons, then it's +2. Let me just try a different one with you real quick. Don't write this one down. Let's say that we were doing nitrogen. What would nitrogen look like? So right off the bat, how many protons does nitrogen have? Okay, so 7 protons. So in the first energy orbital, there would be 2 electrons. And then how many in the second orbital? 5. Yeah, because you need to get to 7, right? So 1, 2, 3, 4, 5. I actually don't really care where you put them. So there's the picture for it. And then for the dot diagram, nitrogen needs 5 electrons around it. It usually would be drawn like this. You'd spread them out, 1, 2, 3, 4. But then because there's a 5th one, we just need to pair one of them up. And so I don't care which one, but you do something like that. And then see how there's 1, 2, 3 electrons left over? That's why nitrogen often has a -3 charge. Because it needs to find an electron to go here. It needs to find an electron to go here. It needs to find an electron to go here. So if it can find 3 more electrons, then it's full up. Do you guys recall doing this at all? A little bit. Okay. Anyways, that's what I'm looking for when I ask you to draw the dot diagram. So last little bit here, the number of valence electrons. Well, the answer to that is, well, how many dots did you draw around the thing? If you draw 1 dot, it has 1 valence electron. If you draw 6, it has 6. Does that work? Okay, let me do one more thing here. I'm going to skip down a little bit here. Number 4. For the following compounds, I want to try to figure out whether it will dissolve in water or not, and name the compound. What is it going to take for it to dissolve in water? It needs to be what type of compounds dissolve in water that are electrolytes? Ionic. Yes, ionic. Yeah, that's basically it. If it's an ionic compound, it dissolves in water. So let's practice these. NaF. Ionic or covalent? Is there a positive and a negative, or just negatives? Yeah, because sodium's on one side, fluorine's on the other, right? So this is ionic, so therefore it will dissolve in water. And then we just name it. So how do you name NaF? You got it. Good job. Yeah. These are the things I need you guys to get working on, so that you're fairly fluent in that, because I think that's the biggest thing that hampers kids' success, right? If you can't look at NH4 and just know that it's, or NaF and know that it's sodium fluoride, and know that it's ionic, then it puts you behind the eight ball. So we'll work on it. Let's try the next one, CH4. Anybody know what CH4 is? It's got a special name. Jason, you better go up there. Yeah, it's methane. It's methane gas, CH4. It has a special, unique name. Now, You know how I know hydrogen gets written on that side of the table over there, but hydrogen is considered to be a non-metal. So you have a non-metal of hydrogen, you have a non-metal of carbon. That's not an ionic compound. It's actually covalent, so this thing will not dissolve in water. Which kind of makes sense. If you were to bubble gas through water, it doesn't dissolve. Kind of a gross example, but anyone ever been in a hot tub and someone maybe lets out some flatulence? That's methane gas. Does it dissolve in the water or does it bubble to the top? It bubbles to the top. It doesn't dissolve in water. So that gas does not dissolve in water, so therefore the answer to this one is no, it will not dissolve, and its name is just a special. Does that help a little bit? Okay. If you guys want to take a quick little break, because I talked you through for most of the time here, why don't you guys start working on this assignment as well as your lab? And I can print you that lab as well, actually. And those will be some of the first things that we'll work on. So then tomorrow we'll do another set of notes, and then after tomorrow you should be able to do this whole assignment actually. So, but most of the second half of the assignment is tomorrow's lesson. So, Wednesday we'll have a work day. Thursday we're going to do our activity. If I didn't point this out, by the way, sure I did. We're doing a quiz next week though. So what I'd like to recommend, try to finish this assignment by at least next week Monday. That way you're prepped for your quiz, right? If you don't do it by next week Monday, then you're not ready for your quiz. Sound good? Okay, take a little break, and I'll see that I can get you guys those grades from this thing here. I can figure out how to fix that thing.